In our last lesson, we saw what systems look like when they're graphed that have infinitely many solutions. That was where the lines were in the same spot. They had the same slope and the same y-intercept. And then we also saw what no solution lines look like when they're graphed. They have the same slope but different y-intercepts, so they were just parallel lines. So what does that look like if you're not graphing the lines? Algebraically, how can you figure out if you have infinitely many or no solutions to your system? So I would like to show you how you can tell. We're going to solve these systems just like we normally would. If we're using substitution, we will isolate a variable. Oh, look, this y is already solved for y equals. So I'm going to go ahead and put a box around what y equals. I'm going to take that and substitute it into the other equation for the y. And then I rewrite the equation. 6x minus 2 times, in parentheses, 3x plus 1 equals -2. Let's go ahead and start solving. I'm going to carry down the 6x. We are distributing a -2. -2 times 3x is a -6x. -2 times 1 is a -2. And then combine like terms. So 6x minus 6x is actually 0. So our variable that we're solving for has gone away. We have nothing to solve for. We don't have an x to solve for. The y, we substituted it in, so we don't have a y in this equation. And when this happens, when your variable cancels away, whether it's the x or the y, and you have no variables left in your equation, you're going to carry down everything else that you have left over. We have a -2 on the left. Here's our equal sign. We'll carry that down. And we have a -2 on the right. We want to look at this final statement and determine if this is true or if this is false. Does -2 equal -2? Because that's a true statement, that means that solutions exist. And that actually means that all of the solutions exist that are on these two lines. So this is your infinitely many, if I can spell it right, let's see. Here we go. Infinitely many solutions. Every single point on these lines is a solution to both equations. If they were graphed, these two lines would be the same line. All right, so that's what happens. Our variable cancels away. You have nothing to solve for. Carry down what you have left over. See if that's a true statement or not. All right, let's try another one. We have, in our next example, we're looking for a lonely variable. Oh, we've got a y equals on the bottom, so y equals 5x minus 4. We're going to substitute that in for the y. So we have 5x minus, we're going to put parentheses around what we are substituting in, right? The parentheses in this case are important, even though we just substituted in for a y. That y didn't have a number in front. Really, it's like there's a -1 in front of that y. So that is a -1 that we're going to end up distributing. We're going to carry that first 5x down. Let's distribute this negative. So -1 times 5x is -5x. -1 times a -4 is a +4. And then carry down the rest of your equation. Combine like terms. Well, we have this 5x minus 5x, so our variable cancels again on us. It could be x's, it could be y's, whatever's in your equation. If it cancels away, you don't have a variable to solve for, so you carry down the rest of your equation. We have +4 equals -4. Then we ask ourselves, is that true? Does 4 equal a -4? And that is not true. That is false. So if you have a false statement after your variables cancel, this is a no solution system. If we were to graph these two lines, they would be parallel. They would have the same slope but different y-intercepts, which is why there is no point of intersection. There's no solution, no point that is on one line and also on the other line.